section 11.7 deals with events involving and also conditional probability. And also, it's not part of the title of this section, but we're also going to see the at least one formula. So 3 more formulas in this section, in this chapter. So this is broken up into 2 videos. So this is just the part 1 video. In this first video, we're going to focus on the and formula. Please, 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 after you get done watching this video, please watch the part 2 video where we will cover the at least one and the conditional probability formulas. So 2-part video. Okay, so for part 1, we said we're going to focus on the and formula. And the and formula means we are going to multiply. So you're going to take the probability of event A and you're going to times it by the probability of event B. However, this formula is so misleading. The title is what's misleading. They call it the and formula, and I really don't like that all these math textbooks call this probability of and, because the and is implied. So I'm going to scribble out the word and. It's not like with the or formula where you literally saw the word or. If you happen to see the word and, it's just a coincidence in the examples to come. So you might be going, but how do I know when to use this formula then? How do I know when to multiply? So you're going to have to read these questions very carefully. And whenever you're selecting 2 or more items, that's when you use the and formula. So whenever you're selecting 2 or more items, then you know at the very least you're going to be multiplying. However many items you select, that's how many fractions you multiply. So if I'm selecting 2 cards, I'm going to multiply 2 fractions together. If I'm selecting 3 cards, I multiply 3 fractions together. If I'm selecting, they love using donuts and food examples in the homework. So if I'm selecting 2 donuts, I'm going to multiply 2 fractions together, and so on and so forth. So again, however many items you're selecting, that's how many fractions, how many probabilities you multiply together. So now that we know, don't look for the word and, look for how many items you're selecting. Let's take a look at example 1. 2 cards are to be selected from a standard deck with replacement. Determine the probability that 2 spades will be selected. So already I know it's time to use our new formula, the multiplying probability formula. How do I know that? Because how many cards am I selecting? 2. This is the first example of this whole chapter with probability where I'm actually selecting 2 items rather than just 1 card. Because I am drawing 2 cards, I'm going to multiply 2 fractions together. With replacement, so we can always assume whenever you're drawing 2 or more items that you pick up 1 at a time. And with replacement means after you draw each card, it goes back into the deck. So you can pretend it really says with replenishment because you're replenishing the deck. So with replacement, each card goes back into the deck. And so with replacement means you could potentially draw the same card over and over again, since you've put each card back into the deck before your hand goes in to pick up the second card, and so on and so forth. So keeping that in mind, we want the probability we get 2 spades, and whenever I multiply, and I was doing this when we counted way back several sections ago in that video, but whenever I multiply in this chapter, I like to draw underlines just to help me visualize the scenario better. So if I'm looking for 2 spades, I'm going to draw 2 underlines. Let's put the times symbol in. We know we're going to multiply. And so each underline in my picture represents a card. So I drew 2 underlines because we're drawing 2 cards. And I labeled what we want. We want a spade for each card. So we're going to take care of each underline one at a time. So my hand goes in to draw the first card. We're looking for a spade. It's still what we want, what we're looking for. Divide by grand total is how we set up these fractions. So if we're looking for a spade, there are 13 spades in a standard deck of cards divided by 52 total cards. So I've brought up a picture of a deck of cards if it helps to visualize it a little bit better. And we said there are 13 spades because there's 13 cards of every suit. So you have a 13 out of 52 chance at selecting a spade. We always assume we get what we want in probability. So I got one of these 13. That underline represents I picked up one of the 13. It's just the likelihood I pick up a spade is 13 out of 52. If it helps, pick one. So let's pretend I drew the king of spades. With replacement means it goes back into the deck before my hand goes in to pick up card number 2. Now we want another spade. We are back up to 13 spades since I put the king of spades back in the deck out of 52 total cards. So it's the total of what we want divided by grand total that we use in the calculations. Each underline represents a card though. So as you can see with replacement, the grand total, 52, went back up to 52 since the card deck is continually being replenished. So now I'm going to make my graphing calculator do the work calculation-wise. I'm just going to type in 13 over 52 times 1352, and I'm going to reduce it all in the calculator. So typing this in, we had 13 divided by 52 times 13 divided by 52. We're going to use our favorite button for this chapter, the math button. It's already highlighted on frac. Then after we select frac and it comes onto the main screen, hit enter again, and the reduced final answer is 1/16. So 1/16 would be the final answer you would type into the answer box in my math lab. Example 2 is similar, but there's one big difference. So 2 cards, so already I know I'm going to multiply at the very least because I'm selecting 2 items, are to be selected from a standard deck, but now it's without replacement. Determine the probability that 2 spades will be selected. So again, notice you do not see the word and, even though it's called the and formula. I'm going to use the and formula because I'm drawing 2 items. Because I'm drawing 2 items, I'm going to again multiply 2 fractions or 2 probabilities. Without replacement means that each card does not go back into the deck. It's sitting off to the side, so you will never ever draw the same card twice. Each card does not go back into the deck. And we said I'm going to draw my underlines whenever I'm multiplying. And we're looking for a spade followed by another spade. Okay, so without replacement is always going to be a little bit trickier than with replacement. So we're going to take our time. So we want the first card to be a spade. It starts the same way as the last example. So the likelihood the first card is a spade, well, there are still 13 spades out of 52 total cards. I encourage you to pick one because it helps to visualize the scenario better. So I'm going to pretend again I got the king of spades. We always assume we got what we wanted. We wanted a spade, so we got one of these 13 spades. I got the king of spades. Without replacement means the king of spades does not go back into the deck. It's now off to the side, so I will never ever draw the king of spades again. So before my hand goes in to grab card number 2, my spades are down to only 12, ace through queen. And my grand total of cards is down to 51. So it's 13 over 52 times 12 over 51 that you're going to punch into the graphing calculator. Math button, frac, enter. If you type it correctly, you should get 1/17 on the calculator as the final reduced answer. Because I'm drawing the same thing, spade followed by another spade, is why the numerators went down from 13 down to 12 without replacement. However, if I were drawing something totally different, like a spade followed by a heart, like we're going to see in the next example, the only thing I'm guaranteed to have happen when it's without replacement is that the bottom, the grand total, is going to go down. Since the cards are not being replenished, each card is off to the side, it does not go back into the deck. At the very least, the bottoms will go down by 1 when it's without replacement. Whereas when it was with replacement, the bottom, the grand total, stays the same because the card deck keeps being replenished. So that if you're a pattern person, it's something good to note. So the bottoms stay the same when it's with replacement, whereas the bottoms go down by 1 when it's without replacement. Let's try another one of these, actually several more of these, because it's definitely a trickier formula. You got to take your time. So example 3 says that you are dealt 3 cards. So I'm going to multiply because I'm picking up 3 of something. And because I'm selecting 3 cards, I will multiply 3 fractions together this time. In succession means without replacement. So I'm going to draw an arrow to the each card does not go back into the deck. So in succession, or it might say successively in the homework, it all means the same thing. Or in the homework, they love using the donut or the chocolate candy examples. They say you eat it, you eat the donut, you eat the candies. That also means without replacement because the candy, the donuts are not going back into the pack. From a 52 card deck, find the probability of getting a diamond, a spade, and then a heart. All right, so I'm going to draw 3 underlines this time. 1 times 2 times 3, because we're drawing 3 cards. We want the first to be a diamond. We want the second to be a spade. And we want the third one to be a heart. And some people like to take care of the bottoms of these fractions first. That's fine. I'm going to draw my fraction bars. We said in succession means without replacement, where at the very least the bottoms will go down by 1. So we have 52 total cards. After we draw one of those, we'll be down to 51. After we draw one of those, we'll be down to 50. Okay. So let's use the labels of my underlines here to figure out the numerators. So card number 1, we want a diamond. There are 13 diamonds in a deck of cards. So you have a 13 out of 52 chance at scooping up a diamond. 13 out of 52. Again, let's pick one just to visualize it a little bit better. So I'm going to pretend I got the ace of diamonds. Without replacement means it is gone. I'm going to scribble it out. It's gone. It's not going to go back into the deck ever. I will never draw the ace of diamonds again. So now my hand goes in to draw card number 2, which we want a spade. We are down to 51 total cards since the ace of diamond is gone. But since I'm drawing something totally different, I don't want any more diamonds, I want a spade. There are still 13 spades sitting in front of me. Again, I got one of the 13 diamonds. I pretended it was the ace of diamonds in card number 1, but there are still 13 spades sitting there in front of me before I grab card number 2. Again, let's pick one. It'll help to visualize this. So I'm going to pretend I got the ace of spades as my spade for the second card. So I'm going to scribble that out. So before my hand goes in to draw card number 3, 2 cards are gone. Ace of spades, ace of diamonds. So I am down to 50 total cards. However, I want something different now. The categories keep changing, is why the numerators are not going down. And I now want a heart. There are 13 hearts still sitting in front of me because I just grabbed a diamond and a spade as my previous card. So there are still 13 hearts. So this is what I mean by when it's without replacement, you are not guaranteed anything about the tops of these fractions. Notice here I have 13, 13, 13 all across the board. The only thing we are guaranteed is that the bottom, the denominator, is going to go down by 1. So since we're drawing different groups, different categories, is why the numerator did not go down. So you're going to type into your graphing calculator 13 over 52 times 13 over 51 times 13 over 50. And let's see what we get. Putting it in the calculator, so we had 13 divided by 52 times 13 divided by 51 times 13 divided by 50. Math button, frac, enter. Oh. Let's see if it's going to cooperate. We might have to reduce this or multiply it longhand. Math, frac, enter. Yeah, see how it's just not giving us a fraction? So we are going to have to multiply this the old-fashioned way and see if it reduces. So that does unfortunately happen sometimes in the My Math Lab homework. When that does happen, we will multiply across the numerators and denominators separately. At least the good thing about multiplying fractions is they do not have to have the same denominator like if we were adding or subtracting fractions. So let's start with the numerators. So first, in your graphing calculator, you would do 13 times 13 times the other 13, or 13 raised to the third power. And when you do that, you get 2,197. 2,197. On the bottom, we had 52 times 51 times 50. So putting that into the calculator, that's 132,600. Then we would test to see if any number besides 1 divides into the top and bottom. What do I mean by that? So it's guess and test on the calculator, and you see if you try to divide into the 2,197 and into the 132,600, do I get a nice non-decimal answer, a whole number? Meaning no remainder? If so, that's how we know it's divisible by that. So like if I try 2,197 and I try dividing by 3, it's not divisible by 3 because I get 732.3333, so on. So because I get a decimal when I try dividing by 3, it's not divisible by 3. And when we try this even though the bottom, the 132,600, is divisible by a bunch of numbers, it's divisible by 5, 10, and 2, for example. We'll give you a nice whole number out. The 2,197 on the top is not divisible by those same numbers. So because only 1 divides into the top and bottom, as horrible as this looks, this is the simplified final answer. 2,197 over 132,600. There are some weird fractions, unfortunately, as final answers. Most of the time the calculator will cooperate, except for with some of these weirder answers. Let's try a few more examples with the AND formula because it is a trickier formula. So example 4, 3 people are randomly selected. So already I know we're going to be using the AND formula because we're talking about 3 people. So I'm going to have to multiply 3 fractions together. 1 person at a time from 5 freshmen, 2 sophomores, and 4 juniors. Find the probability that the first 2 people selected are freshmen and the third is a junior. Okay, so let's get this set up, ready to go. Yes, we saw the word and, but that was just a coincidence. The and is usually implied. It's usually, the implication is the first person is a freshman and the second person we select is a freshman and the third person we select is a junior. So that's how, when you're selecting multiple items, that's how the and is implied, by the way. So we said 3 people were selecting, so I'm going to draw 3 underlines. With multiplication, we know whenever we're selecting 2 or more, we multiply. And I'm going to label my underlines. So they want the first 2 people to be freshmen and the third person to be a junior. Let's try to figure out if this is with or without replacement. It does not specify. So if you're selecting one item at a time like this, if you're selecting one person's name at a time, you can assume it must be without replacement. In other words, I'm not going to select the same person's name twice. So without replacement, that was where the denominator, the bottom of the fractions, goes down by 1. So I'm going to write den for denominator and a down arrow here. So at the very least, the denominator will go down. So how many total people are there? Well, let's see. There were 5 freshmen, 2 sophomores, and 4 juniors. So when I add that together, 5 plus 2 is 7, plus 4 is 11 total. So before my hand goes in to select the first name, there are 11 total people. Since it's without replacement, when I go to select the second name, I'll be down to 10 people. When I go to select the third name, I'll be down to 9 people's names. They don't give you the total. As you just saw, we just simply add all the outcomes together. And then we use the labels of my underlines to figure out the numerators, the tops of these fractions. So how many freshmen? Well, there are 5 freshmen. We always assume we got what we wanted, so we got one of those 5 freshman names. So before my hand goes in to draw the second freshman's name, I'm down to 4. So maybe I should draw a picture down here just to kind of explain it a little bit better. I'm going to abbreviate a little bit. So there's 5 freshmen, 2 sophomores, 4 juniors. I draw, my first name is a freshman name. I'll put a little X there. The second name I draw is another freshman's name. So I'm down by 2. So I don't have 5 freshmen anymore. If I've drawn 2 freshman names, 5 minus the 2 means I am now down to 3 freshman names. So my total is down to 9. 3 plus 2 plus the 4. But now I want something different for the third name. I want a junior name. There are still 4 juniors' names. sitting in that pool of people. So you have 4 out of 9 chance at getting a junior name. So we got 2 freshman names and 1 junior name by the end of this draw. And now we multiply these fractions together. So 5/11ths times 4/10ths times 4/9ths. If it helps, maybe you want to draw a picture. So again, at the total, we had 11 total people. We had 5 freshmen. We had 2 sophomores. I'll just put soph for sophomores. And we had 4 juniors. We wanted the first name to be a freshman's name. We always assume we get what we want in probability. So I'm going to put a little check here. So we got one of these 5 freshman names. The probability you get a freshman name is 5 out of 11. So if you got one of these 5 freshman names, then you're down to 4 names before you draw the second name. We want another freshman name, so we said we're down to 4 freshmen and we're down to 10 total people. We got what we wanted, so we got another freshman name, which means we're down to 3. Our hand goes in to draw the third name. Now we want a junior's name. There are still 4 juniors, but there are only 9 total. So 4 out of 9 is the third fraction to multiply. And I would just punch it right into the graphing calculator, and let's see if it's going to cooperate on this example. So we had 5 divided by 11 times 4 divided by 10 times 4 divided by 9. Math button, frac, enter. 8/99 is the final answer. So jotting that down, 8/99. Example 5. Each question of a 5-question multiple choice quiz has 3 possible answers. Suppose a student picks an answer at random for each question. So they just Christmas tree it, in other words. Find the probability that the student selects the correct answer on only the second and third questions. Okay, so we are talking about 5 questions. The probability with a specific scenario of how the student answers 5 questions. So that's how I know it's the AND formula, or what I call the multiplication probability formula. So I'm going to draw 5 underlines because we are going to multiply 5 fractions together, is what that means. So 1 times 2 times 3 times 4 times 5. And it says they want the probability that the student selects the correct answer on only the second and third questions. So my second underline, I'm going to label correct. And the third underline, representing the third question, I will also label correct. Whereas that implies if questions 2 and 3 are correct, questions 1, 4, and 5 must all be wrong. Let's put just W's, how about for wrong, since as usual I'm running out of room here. There we go, and I'll put just C's for correct. Let's do a different color for correct. All right, so we're looking for this exact scenario to play out. So they just guess, they Christmas tree it, and they get question 1 wrong, question 2 correct, question 3 correct, question 4 wrong, and question 5 wrong is really what this question is saying to us. And if it helps, feel free to draw a picture. So they said there are 5 questions. Each question has 3 possible answers. So an A, B, and a C for each question. And in my picture, I'm just going to pretend that C is always the right answer. All right, so let's start with question 1. what we want, what we're looking for, divide by grand total. So if we're looking for a wrong answer, 2 out of the 3 choices are wrong. Because there's always one correct answer. So that means all the remaining choices, which would be 2, are wrong. We want question 2 to be correct. So I'm going to pretend C is the correct answer. But the point is that there's one correct answer out of 3 options, A, B, C. Question 3, we also want to be correct. There's one correct answer out of 3 total choices. Question 4, we want wrong. The probability they guessed wrong, in other words. So there are 2 wrong answers, A and B, out of 3 options. And we want question 5 to be wrong. There are 2 wrong options out of 3 total choices. You'll notice that the denominators are all 3s. In this question, they did not go down. It's similar to a with replacement scenario. More specifically, these are independent events, is what we would say in probability, meaning if you guessed right or wrong on question 1, has no effect on if you get question 2 right or wrong. Each question is a totally separate, independent question. It does not affect how you answer the other questions. So this is independent. With replacement that we talked about on the last slide is an example of independent events. But with independent events, the denominator, the bottom of the fractions, will stay the same. They do not go down by 1 like without replacement or dependent events would. So now it's just a matter of seeing if the calculator is going to cooperate. If it doesn't, we will type it in longhand. When you punch this one in, it does cooperate in the calculator. Yay! Just make sure you hit math, frac, enter, and you'll get 8 over 243 as the final answer. If the calculator did not cooperate, meaning it just gave you a decimal, no fraction, even after you hit the math frac button, you would just have to multiply the tops together. So 2 times 1 times 1 times 2 times 2, which gives us the 8 on top, and then the bottoms together. 3 times 3 times 3 times 3 times 3 is 243. If it reduces any further, you would want to do so. This one does not reduce any further. A couple more examples. Example 6, we said they love using food examples. In the My Math Lab, you'll see some chocolate candy examples, some donut examples. So remember, whenever you're selecting 2 or more of these food items, that's how you know when to multiply, at the very least. So there are 30 chocolates in a box, all identically shaped. 5 are filled with coconut, 10 with caramel, and 15 are solid chocolate. You randomly select one piece, eat it, and then select a second piece. So you're selecting 2. Find the probability of selecting 2 solid chocolates in a row. So because I'm selecting 2 candies, that's why I'm multiplying. And if I'm selecting 2, that means I need to multiply 2 fractions together. We're looking for solid chocolate, followed by another solid chocolate. Because you're eating each piece after you select it, this is an example of without replacement or dependent events. Dependent events, meaning the bottom of these fractions is going to go down by 1. The denominator, I'll put den for denominator again, goes down. You'll never select the same piece twice if you're eating it. So we want a solid chocolate. There are 15 solid chocolates out of 30 total. You got one of those 15 solid chocolates. You ate it. So before you grab candy number 2, you're down to 14 solid chocolates, and your grand total went down from 30 to 29. The top, the numerators happen to go down as well because you're drawing the same type of candy over and over again. Solid chocolate followed by another solid chocolate. So when you punch in 15 over 30 times 14 over 29 into the graphing calculator. Math button, frac, enter. You will get 7 over 29. If you're trying to find this example in my lecture note packet from my face-to-face version of this course, this is listed as on the second page from the end under the extra practice part, by the way. But 7 over 29 is the final answer. Same question, but B says you want a coconut-filled chocolate followed by a caramel-filled chocolate. Same idea. You are still grabbing 2 candies, so you're going to multiply 2 fractions. And we said we're looking for a coconut followed by a caramel. Coconut, there were 5 coconut out of 30 total. You eat one of those 5 coconut that you just grabbed, so your total is down to 29. However, you got a different type. The second candy is caramel. If you grabbed a coconut on your first draw, you still have all 10 caramel sitting in front of you. Remember, you get what you want in probability. You got a coconut, so you still have all 10 caramel available when you draw candy number 2. So 5 out of 30 is the probability you get 1 coconut, times 10 out of 29 remaining candies is the probability you get a caramel. When you punch that into the graphing calculator, math, frac, enter, you get 5 over 87 as the final answer. And finally, example 7, you can find this also in the extra practice section of my note packet, which I've uploaded in Canvas. It's on the very last page. 2 marbles, already I know we're going to multiply because I'm drawing 2 of something, are drawn without replacement from a box with 3 yellow, 2 green, 2 red, and 1 blue. Find the probability that the first marble is red and the second marble is green. So I'm going to draw 2 underlines since we're drawing 2 marbles. We want the first one to be red, and we want the second marble, which would be the second underline in my picture, to be green. Let's see, they did not give us the total number of marbles, so we got to add everything ourselves. So there were 3 yellow, there were 2 green, 2 red, and 1 blue. So when I add that up, 3 plus the 2 would be 5, plus the 2 is 7, plus 1 is 8. There are 8 total marbles. Without replacement means after I get one of those 8, I will be down to 7. The denominator goes down when it's without replacement. First, we want a red marble. There are 2 red, so you have a 2 out of 8 chance at getting a red marble. You'll get one of those 2 red. It's off to the side, but be careful here. You still have 2 green sitting in front of you. If it helps, draw a picture. So we said we had 3 yellow, so I'm going to write Y for yellow. We had 2 green, so I'll write 2 G's here. We had 2 red, so I'm going to draw 2 R's. And we had 1 blue, so 1 B. We first want a red marble, so I'm going to X out one of these red, these are marbles. It's off to the side. Remember, without replacement means you will never draw the same marble twice. So before my hand goes in to draw the green marble, my total is down to 7. However, I still have 2 green sitting there because you got a red. You haven't grabbed a green yet. So there are 2 out of 7 is the likelihood you get a green marble. You get one of those 2 green. So you're going to type in 2 8s times 2 7s into your graphing calculator, math button, frac enter as usual, and you should get 1/14 as the final answer if you do it correctly. Please watch the part 2 video. This is of the same section, but I'm going to go over 2 different formulas, the at least one and the conditional probability formulas. Hang in there. We are almost done with chapter 11 if you are not a fan of all of these formulas.